In this video, we're going to discuss the first of our cosmic distance ladder series of labs, the one dealing with parallax. Parallax is a distance measurement technique that, believe it or not, you probably use all the time in your everyday life. In order to complete this lab, we're going to need a little bit of equipment. We will need a protractor with an attached string, and we're going to need a tape measure, and we're going to use parallax as a technique to get some distances to some nearby, or at least relatively nearby, objects. Getting the distance to extremely distant objects is actually one of the hardest things we ever do in astronomy. For things nearby, you can just use a tape measure or a ruler to get their distance, but when you're talking about objects that are thousands, millions, maybe even billions of light years away, that simply becomes impractical. So we have a variety of techniques that we use to try and figure out the distance to these very, very distant objects. Parallax is just one of these, and it forms one of the early steps in what's called the cosmic distance ladder. So we use measurements that we know here on Earth that we can actually measure with a ruler to then work our way up to Earth baseline parallax, then stellar parallax, and then later we'll use variable stars, supernovae, and some things from Hubble's law in cosmology to actually get distance to even further objects. But we use the earlier sections to calibrate the later sections. So parallax is kind of the earliest, or at least one of the earliest rungs on this distance ladder. So I said that you probably use parallax in your everyday life without even realizing it. So most people have two eyes and have binocular vision, and binocular vision lets you do things like estimate the distance to objects. So when you're trying to catch a ball or when you're trying to figure out if something is closer than something else, your brain is actually getting two images. It's getting an image from your right eye and an image from your left eye. And your brain can actually figure out, based on how much the objects shift between those two things, it can figure out the distance to an object, or at least that's one of the ways that your brain is computing the distance to an object. So one thing you can do to kind of illustrate this to yourself is you can take a pencil or your finger and you can hold it out at arm's length, and you can use it to cover up something in the distance, say a lamp on a desk or a light switch on a wall, and you can close one eye. So close your left eye first and line up your finger with some object on the other side of the room, and then leave your finger in the same place, but open your left eye and close your right eye. And it looks like your finger has shifted. To kind of illustrate that, here's a picture that shows you what that would look like. So imagine that you're holding your arm out or your hand out at arm's length, and you line up your finger with some tree in the distance with your right eye open. If you close your right eye and open your left eye, it's going to look like your finger has shifted. Now, nothing has really moved. It's just your perspective has changed. The place that you're observing from has changed. So how much has it changed? Well, in this case, you've shifted from looking from one position where one eye is, looking to the other position where the other eye is. So the amount that you've changed, the distance between those two observations, we call that distance the baseline. And if you wanted to, you could measure the distance between your eyes and then figure out how far away something is based on how much it appears to shift. So what we're going to need to be able to do in this lab is measure a baseline somehow, and then measure a change in angle somehow. And that's where the protractor and the tape measure are going to come in. We're going to measure our baseline with the tape measure. We're going to measure the angle change with our protractor, and we're going to use that to calculate the distance using some geometric relationships to measure the distance to some objects. Now, just using the distance between your eyes is probably not the best way to observe objects at really, really great distances. As we'll find out in just a minute, the distance of your baseline, the size of your baseline, dictates how much the object is going to appear to shift. So the bigger the baseline, the larger of a shift you will see. So we'd like to be able to measure distances to very, very large objects, so we're going to need to be able to measure actually relatively small angles because the distance to the object also changes how much it appears to shift. And you can actually, again, simulate this yourself. So you could do that same trick with shifting your eye left to right and looking at distant objects and nearby objects. You could change how far out you have your arm, for instance. So if I were to set an object here, if I were to set my finger here at arm's length all the way out, I can see one shift looking at a distant object. But if I bring my finger much, much closer to my face, repeat the procedure, you'll see that your finger appears to shift by a much larger distance. So this shift that we see depends both on our distance to an object and the size of our baseline. So we want to maximize those things if we can, or at least maximize our baseline to get a good shift in angle. So one of the types of parallax that we can see is something called Earth baseline parallax. So imagine that I have two observers, one on one side of the Earth and one on the other side of the Earth, and they're both looking at some object in space, say a spacecraft or a satellite or the moon, something relatively nearby compared to the background stars. So the person at position A looks at that object, and to him, it appears that it's over here somewhere relative to those background stars. Because we're looking at this object that's very distant, we can't actually see exactly where it is. We don't know how far away it is. But just looking from our vantage point, it looks like it will be lined up with these stars over here. So if they took a picture, it might look like this. Meanwhile, the person at position B, over on the opposite side of the Earth, he's looking at the same object, and to him, it looks like that object is in front of these stars here in the background. So for the person at position B, instead of seeing that object over here, they see it over here, so we can actually see a shift between where A sees the object and where B sees the object. Now, in this case, we'd like to know the baseline between these two observations. What's the distance between the observation at A and the observation at B? That's our baseline. Well, that happens to be the diameter of the Earth, because we have someone on one side of the Earth and someone on the other side of the Earth. So this gets us a much, much bigger baseline than just closing one eye and then opening the other eye. So this is a much better technique for trying to get distant objects. Now, we can actually go one step further than that. We could do stellar parallax. So now, instead of having an observer on one side of the Earth and an observer on the other side of the Earth, what if we just waited for the Earth to move? Remember that the Earth is orbiting the Sun. So the Earth is making a trip around the Sun once a year. So we could take an observation, say, in January, and then we could wait 6 months until we've gone halfway around our orbit, so sometime around July, and we could take another observation. So now our observations aren't simultaneous, but we took one here, and then we waited 6 months, and then we took another one over here. And some object, now we can look at a much more distant object because we have a much larger baseline than just the size of the Earth. In fact, our baseline now is the diameter of the Earth's orbit. And by the way, here's a point that can be fairly tricky for students. This baseline is not the radius of Earth's orbit, but it's the diameter of Earth's orbit. So we know that the Earth orbits at a distance of 1 AU from the Sun. So it went to the other side of the Sun, so it's now 2 AUs from its original position. So keep that in mind when you're doing your calculations. But now our observation in January to some star that's, say, relatively nearby, well, it will move compared to stars that are very, very distant. So our observation in January might have that star over here, and our observation in July will have it over here somewhere. So it will shift by some amount in the sky, and by measuring that shift, we can figure out how far away the star is. So to do all of this, we're going to have to do some math. So there's an equation that will come up again and again and again as we do both parallax and moving forward with some other things later in the lab. And that's this equation that we're using right here. So for an Earth baseline parallax, or even for a stellar parallax, it's essentially going to be the same equation, but we're going to change what some of the terms mean. So imagine that this blue dot here is the Earth. And so in my first example up above, where we were using the Earth baseline parallax, now I have an observation from one side of the Earth and then an observation from the other side of the Earth. And both of these observations are looking at this same object here. And imagine that I have background stars back here that I can compare them to. So one observation is going to see that object over here. One observation is going to see that object over here. Well, what we can actually do is set up a ratio. So imagine that this black line here is a complete circle. So imagine that it goes all the way around. The baseline is some fraction of that total circle. So this baseline, we can measure this distance. This total circle here, well, we can compute the circumference of a big circle, right? The circumference of a circle is 2 pi times the radius of the circle. Well, the radius of this big circle is the distance from Earth to this object that we're looking at. So that's the distance that we're trying to measure in this case. We're trying to get that r. So our baseline is some fraction of this total circumference. So our baseline is some fraction of the total circumference of this big circle all the way around. Well, we could compare that fraction to the fraction of this angle that it's shifting by. So we look here and we see this object relative to background stars, and we look here and see this object relative to background stars. So we can measure some angle between those two positions. And this angle over here on the right-hand side is the same as this angle over here on the left-hand side. Those are similar angles. So this angle is the same as this angle. We're going to call that angle theta, and we're going to call that our angular shift. So how much that object seems to move by. So if it appeared over here in our first image, and then it's moved over here in our second image, we can measure the angle between these two things. That's going to be our angle theta. Well, that angle theta is some fraction of a total circle, and a total circle is a full 360 degrees. So this theta is some fraction of 360 in the same way that our baseline is some fraction of this big circle all the way around, this 2 pi r. So we're going to use that ratio, that comparison of our angular shift to 360 degrees to our baseline to this full circumference of a circle. We're going to use this to calculate that distance r. And so for Earth baseline parallax, we know that this baseline is going to be the diameter of the Earth. Well, similarly, for stellar parallax, we could use that exact same equation, and we could now say that this baseline is now the Earth orbiting around the Sun, rather than the full diameter of the Earth. It's now the diameter of the Earth's orbit, so that's our baseline. But it's the exact same argument that we just made. This baseline is some fraction of this total circle in exactly the same way as this angular shift theta is some fraction of 360 degrees. So writing this equation here out in a little more clear fashion, it looks like this. Our baseline over our circumference is equal to our angular shift of theta over 360 degrees. But again, our circumference is just 2 pi times the radius, and the radius is the distance between us and this distant object. So the distance is the thing we want, so now we can solve this equation for distance, and this is just rearranging some terms algebraically. So our distance is now equal to our baseline over 2 pi times 360 degrees over theta. Now, a word of caution. We will often measure theta, because this theta is usually going to be fairly small when we're dealing with stellar parallax. We'll often measure theta in arc seconds or arc minutes. It will be a very, very small angle. Before you put that theta into this equation, make sure your theta has been converted to degrees. Because we have 360 degrees here in the numerator, we're going to need degrees in the denominator so that these two terms cancel out on their units. So make sure you put your theta in degrees, otherwise this equation is not going to work out well. Because we want our distance to be in some normal unit of distance, meters, AU, kilometers, whatever it is we happen to be using. Well, if our baseline is in those units, 2 and pi are just numbers, there are no units there, and if we have degrees over degrees, those units will cancel. So whatever units we use for our baseline, those will be the units for our distance as well. So keep that in mind when using this equation. Now, how are we going to do this here on Earth? Well, here on Earth, if you're in lab at UNC, we actually have a fairly straightforward procedure with a couple of objects that we know the distances to, and you'll be taking some observations from the top of Chapman Hall on the observing deck. And so what we're going to do is we're going to stand at this rail up on the observing deck, and we're going to take one observation from the far left-hand side on the roof, and one observation from the far right-hand side on the roof. And we're going to look at some objects. And the first one we're going to look at are some smokestacks on the building across the way. The second one we're going to look at is the water tower off in the distance. So what we can do is take our protractor, and we can line it up with the edge of the wall so it's nice and flush, so we always keep it repeatable. And we can point the string toward the object, toward either the smokestacks or toward the water tower, and we can read off an angle on this protractor. So we can see what the angle is when we're observing it from one side and what the angle is when we observe it from the other side. So we can actually work out the first angle and the second angle, and we can work out a shift in angle between them. So this is us essentially measuring theta. So we now have in our equation, we have theta, we want distance, 2 and pi are a number, 360 is a number, so the only thing left is our baseline. So the next thing we need is the baseline, the distance between where we made our first measurement, somewhere over on the left-hand side, and where we made our second measurement, somewhere over on the right-hand side. So we can use a tape measure or a meter stick to actually measure the distance between those two things. That distance is our baseline. So now we have our baseline, we have our theta, we can calculate distance. And that's what we're going to do first for the smokestack that's relatively nearby, and then for the water tower, which is more distant. Now, if you're not at UNC, or if you're taking this lab online, you're going to need to figure out a way to essentially simulate what we're doing here. So your best bet is to try and find a fence or a wall, something that you can line up your protractor with to measure the distance to a couple of objects. And the two objects that you want to try and measure distances to, since you don't have a set smokestack and water tower like we do that we know the distances to, you're going to need to try and pick some objects that are distant but not super distant, because you will need to try and measure the actual distance to them some way, probably with a tape measure. But you do want to try and get two objects that are at least further away than the size of your baseline. So whatever your distance between your two observations is, try and find objects that are at least further away than that. So something that is at least several hundred feet away, maybe around 1,000 feet away for the more distant object. So you want to try and get two objects that are distant that way. Now, there are a couple of interesting ways you can do this if you do want to try and find something that's more distant than you just want to take the patience to measure with a tape measure. You can try and estimate the distance a couple of ways. One thing you can do is if you bring up Google Maps in a web browser, here I've moved us to Chapel Hill's campus at UNC Chapel Hill, and let's say that I wanted to measure the distance between, say, the School of Education and over here the Department of Computer Science. One thing you could do, if you look down here in the left-hand corner, there's a little scale. And the little scale is telling you that between this black mark and this mark over here, that this distance is 50 feet. And so what you can do is measure what this distance is here. Just using a ruler. Put a ruler against your computer screen. You can measure this in inches or in centimeters. And then you can measure the distance from, say, the roof of the School of Education all the way over here to the Department of Computer Science. You can measure that with your ruler as well. And you can compare this measurement to this one. So let's pretend that this is, say, 1 inch. 1 inch is now 50 feet. And if I measure this to be, 4 inches or so, it's going to be 200 feet. So you can convert that way just by using a map or by using Google Maps. If you want to get even fancier than that, you could try and get Google Earth. So Google Earth is very similar to Google Maps. And here again, we're on Chapel Hill's campus. So if I wanted to measure those distances, there is a tool for doing that. And if you click here, it says Add Path. That's going to bring up a little window that lets you add a path. And if we bring up measurements, we can make sure that this is set to feet rather than any other unit. We might want it in feet. You might want it in meters, whatever you're going to calculate in. And I could click once here, and I could click once over here, and it's going to tell me that that's 296 feet between those 2 points. Now, these measurements aren't super accurate, but they're probably accurate enough for the purposes of estimating those distances for the purpose of this lab. So why are you going to need those distances? Well, we're going to calculate a distance using our equation here, using our baseline and our theta, and we're going to compare it to the actual distance. So for the students on campus, the true distance to the smokestack is about 360 feet, and the true distance to the water tower is about 2,800 feet. So we're going to measure those using our protractors, and by measuring our baselines, we're going to try and calculate that distance, and then we're going to compare those to what the actual distances are. So we can see how accurate this method is when we're moving to more and more distant objects.
I'm going to talk through the last few sections of the lab. It's mostly along the same concept. All right, we're still doing parallax measurements, but there are a couple technical things that we need to go through, and then one major conceptual hurdle, and then I'll be done talking for the day, and you guys can get working. All right, so the first part, you're asked to measure the distance to an asteroid. So that should be pretty straightforward. You'll notice there's a section on observing an asteroid with Skynet, and it goes through all this rigmarole of scheduling a bunch of observations from prompt and from Moorhead, and then hopefully they line up and you get two that are simultaneous. Well, we did that for you because it's kind of difficult, and would be hard for you guys to all get your own images back. So we have, those will be in the sample images folder for Lab 4, FYI. But what do we know? Okay, so this is similar to the dwarf planet discussion that we went through for Pluto, but what do we know about an asteroid as compared to, let's say, the rest of the background stars that you might see? If you pull up an image of an asteroid, it's moving, right? Perfect. So the first thing we're going to need to do is identify our asteroid. Just like with Pluto, we have some image, and you're going to see a bunch of white dots in there. One of those is the asteroid, but we don't know exactly which one. So the way that we do that is by making a movie. Just like you made the movie in Lab 3. But the process is the same. You need to pull up the alignment tool. You're going to add the files. They're going to be in the sample images folder. Directory, Astro 101 Lab, Lab 4. And there is a folder for Asteroid Fall 2012. And there are two folders in there. One is called Movie, presumably that has the images to make the movie with, and one is called Parallax, that has the two images that you'll need to make a parallax measurement. So you're going to pull up the alignment tool, you're going to open up all these images, and you're going to do a 1-star alignment with them. This should be pretty familiar from last time, but it should all be the same. Read the directions carefully, and you're going to select an object in here to align to, and then go through the steps, click the same object every time, etc. Okay. So once you've aligned them, you're then going to pull up and make a movie, and just have an example. This is from a previous year's images. This is not exactly what yours will look like, but you should see something like this. And if you watch that loop a few times, you see that one object is moving. Anybody pick it out? It's the bright one in the top right. Okay. So in this case, it was the brightest thing in the field, but that won't necessarily be the case for you guys. So that's the first part. You're just going to need to identify the asteroid. So you just make your movie, and presumably if there's one thing moving, that is your asteroid. What if everything was moving? What do you think happened? You did a line, but... Correct. So what you noted correctly is that if we had a line to this asteroid, instead of it being the only thing moving, everything else is going to look like it's moving, which is actually kind of cool, I think. But either way, you've identified the asteroid, assuming you remember which object you aligned to. And so I know that this is my asteroid, and so when I do the next parts, I'm going to keep that in mind. Okay, I don't need this anymore. All right, so once you know which object is your asteroid, you need to make a parallax measurement. So what do we need for a parallax measurement? We need two things. Baseline and angular shift. Perfect, thank you. So they're going to tell you what your baseline is. Like I said, we don't have telescopes on the equator at opposite sides of the Earth. We have them at CTIO, and you used the Moorhead Observatory for these images. So it's going to tell you this is the fraction of the Earth's diameter that your baseline is. You measured the Earth's diameter in Lab 2, so you're going to enter that value here. Just remember that in case you want to look that up first before you start putting things in. And then you're going to get an actual diameter for your baseline. So the next thing we need to know is the angular shift. And the way we do that is by doing a 2-star alignment. So in this case, we want the entire background to be lined up. And hopefully, if we stack two images taken from different sides of the Earth, you should see that the asteroid moves between those two. And so this is also an alignment process, but in this case, you're going to do a 2-star alignment. So in your case, you would go to the parallax folder and select, there's only two images in there. Those are the ones you're going to use for this part. You're going to change the alignment method to 2-star manual. Intersection is still fine. Stellar photometry or centroiding is still fine. Now in this one, I know you didn't see this movie, but this is the asteroid. In general, when you're doing a 2-star alignment, you want to select two objects that are kind of spread out. So I wouldn't want to use these two right next to the asteroid, but two that are kind of, away from the center. You wouldn't want to use one that's right on the edge. Why might I not want to align to this object? Yeah, it may go off the screen. In my prompt image, if the centering was just a little bit off, you wouldn't be able to select this one, and that would be bad news. So in this case, I'm going to use these two because they're spread out a good deal. They're bright. They're pretty obvious. So I'm going to click on the first star in the first image. It'll automatically go to the second one, and then you need to click on that same star. And if you notice, on the right side, its current star has star 1 highlighted. Once I click this, it'll go to the first image again and ask me to select the second star, and the star 2 button will be highlighted. So do that, and then you should end up with your second image. There we go. Having the 2 stars that you want to align to marked. Then, just like with the normal alignment method, you select the target directory, save them there. Okay. After you do that process, you're going to open up the overlay tool, and this is just going to stack them on top of each other. Hopefully, everything, all the stars, including the ones that you selected, will be matched up, and your object, in this case the asteroid, will be a little bit off. We'll have shifted from one image to the next. Okay. Jeez. All right, so once you finally get the 2 aligned images open, this is going to look just like all our other tools. You're going to have the image window on the left, and then kind of your options on the right. This transparency bar will, if you slide it left to right, will change between only looking at one image versus only looking at the other. Somewhere in the middle, you're going to be looking at both of them. In this case, my asteroid is here, so I'm going to kind of zoom in on that. If you notice, even though the brightness values are different, the background stars are in the same place. And so if I just zoom in on the asteroid, oops, this is not a good one to do an example with. You can notice that the center shifts a little bit. It's hard to tell because one's just brighter than the other one, but I can make a measurement of that. Select my ruler tool, click on the center of the object in one image, slide over it so you're on the other one, and find the center in that one. And that's your angular shift. Now, I've done it with this semester's asteroid. It looks a lot better. They're both like the same size, and it's really obvious. Like just part of them looks like a Venn diagram. Part of them overlap, but the rest, you can see that it's moving. All right, so that's the basic idea. 2-star align them, overlay them, measure an angular shift, and you're going to do that like 3 more times. If we get back to the lab, so you have to measure the distance to an asteroid. Then you're going to do the same thing for Venus. The purpose of doing it with Venus is to calibrate the size of the AU. We know that for our stellar baseline parallax, that our baseline is 2 AU, but we don't, that's just like a name. We need an actual value in kilometers. And so we use Venus's orbit. We know its period, and so we can use Kepler's third law to solve for its semi-major axis. If we then observe it at some point, I'm kind of brushing over this, but please read through it. It's actually pretty good background information. We have an image of Venus with this phase. We know where it is in its orbit based on that. And from that, we know that it is 1.34 AU away. So if we know it's 1.34 AU away, and we have an image to make a parallax measurement of, we can get the actual distance in kilometers and solve for what the value of the AU is in kilometers. And so that's the same basic thing. You're making an angular shift measurement. You're using your baseline and that measurement to find a distance. You're then using that distance to find the size of 1 AU, which you then need for the last section when you're calculating the distance to Alpha Centauri using stellar parallax. You need to know how large an AU is so that you know how large your baseline is in kilometers in order to get that final distance measurement. One other thing to note, Alpha Centauri is a double star system, so your images are going to show 2 objects. It doesn't matter which one you measure the shift of. I think the bigger one's probably easier, but they should be the same. Okay, I think that's